Right. This is the last keynote lecture for this workshop, and then after this, we're going to do the small group discussions, breakout sessions. So one of the things that we talked about yesterday, we identified as one of our objectives as a potential breakout group, was to talk about stage structure models. So what I'm going to do here is just kind of give a really brief overview of some motivating data I found, as well as some modeling approaches that this potential breakout group can take. So I'm sticking with the Daphnia. We're going to talk more about Daphnias here. So Daphnia has a well-documented kind of crazy life cycle. So I don't want to get too much into it right now. These are the pictures that I wanted to maybe have us think about as we talk about a stage structure model. In particular, you have juveniles and adults as the first obvious way to break down a population, or I mean an individual in two different stages. So here you have the juveniles. This is the adult Daphnia, and it has eggs here. There's another stage after the Daphnia is older where they molt. And someone mentioned yesterday, I don't quite remember who, that they had some toxicity that only really showed up during the molting stage. That's why I put this in this last molting stage in here. It's because this might have implications when we start thinking about different toxicants and where the toxicants will have the different effects. And again, this is the context of stoichiometry and toxicology. So we think about the different stressors and if there are any interactive effects of these different stressors. And on top of that, I'm asking, are those interactive effects different at different stages of this individual's life? In particular, you're going to see some data soon that talks about the growth rates of this little guy versus the growth rates of the bigger guy, and subject to different phosphorus levels. And in the context of toxicants as well, how are toxicants going to affect the growth rates? How are toxicants going to affect the timing of maturation? Is it going to be that maturation delay we heard a little bit about from Roger's last talk? Or is it going to affect the number of eggs here? So a lot of different things to consider, and even just considering these first initial stages of the Daphnia. So this is some data from William DeMott in 2003, where here they have Daphnia under P sufficient food, so they have lots of phosphorus here. And it's just tracking the Daphnia's growth, right? So over time, you see going from 0 to 12 days here. Here they have the mass that's given with these data set right here of the circles. So this was a before maturation, and then maturation occurred here, and this when the open circles are there. So that's the mass of the individual. You also have the growth rates. So you can see for the first 6 days or so, it's characterized by a relatively high growth rate. And what happens at maturation is you see this sharp declining growth rate right here to a lower growth rate down here. Okay. So this is where maturation occurred right there. And then this little, between like days 9 and 10 right here, this little disconnect, that's actually the first brood was released. So this is where they had the first neonates were sent out. Okay. But the point here is that you have this, if you were going to think about growth rate of a Daphnia, and a lot of the models we talked about yesterday and I just had a growth rate for Daphnia regardless of what life stage it was in. But arguably, looking at this data set, you have this pretty difference in growth rate depending on whether they're juveniles or adults. So they're going to first stab at making a stage structure model. Maybe we just break them up into juveniles and adults, take these different growth rates. Here we can see, this juvenile has this higher growth rate. The adult, even just assume it's constant, has a growth rate down there. You can also look at the phosphorus content of the Daphnia. And following the growth rate hypothesis, when you have high growth rate, you usually have high levels of phosphorus. And they see that in this data here. The phosphorus content of the Daphnia is up here at pretty high levels, and it declines, and then it's at a lower level. So in the LKE model, this is that theta value that we assume is fixed. We take the homostatic assumption. But if we do a stage structure, we can assume potentially 2 theta values, one for the juvenile Daphnia that's higher up here, one for the adult Daphnia that's lower down here. This is the simplest my first initial thoughts on incorporating some kind of stage structure in here, just to break it up into juveniles and adults. And some of the consequences of this would be that you might be particularly sensitive to P limitation when you're a juvenile, because you have this higher P to C ratio. You have this higher theta value. And so you need more phosphorus. And then under the context of a toxicant or a different contaminant stressor, we can think about how it's also going to be influencing these curves. Is it going to be different for juveniles versus adults? Some more data from the same paper here, but now they have two different phosphorus diets. So here you're looking at Daphnia grown under P-deficient food and P-deficient food. Okay? So the open circles are the low phosphorus treatments. And it doesn't go as long, if you notice, if I go back a slide. This went for 12 days. This next data set they have in the paper is only going for 6 days. Right? So we're looking at the beginning right here. Under the high phosphorus treatment would be this stuff right here. And then this would be what's changing under the low phosphorus treatment. Okay. So, and then you have two different curves here. The solid is growth in terms of mass, and the dashed is when they define things in terms of phosphorus, just if you define things a little differently. So you can see they follow the similar dynamics. So here you have the growth rate under the P-sufficient food, staying up here. Again, this is the first 6 days. So I'm comparing that to what we saw right here with the growth rate around 0.6. So that's what we're looking at right here. And then you can see how the P deficient diet is decreasing that growth rate. And it has a big influence on the Daphnia phosphorus content, as we would suspect. So under the P-sufficient food, it stays up here at that level. But under the P limitation, it's declining down here. So we need to think about some of these assumptions that we're going to make on the P to C ratio if we assume it's homeostatic in the juveniles and adults based off this data. Okay. So this was mentioned briefly a couple times yesterday. I've heard it kind of in coffee group discussions also. I keep hearing the term Hormesis. I hadn't heard of this until I was at the airport on the way here talking with Greg. And we got our flight delayed. We were having a beer, and he talked about Hormesis for a little bit. And so this is new to me. So what this is a more complicated dose response than what I'm used to seeing. And so here you have an experiment where Stanley and others in 2013, they took Daphnia subject to an energetic compound. This one right here, TNT. Right? So here's the dose. And then they're looking at neonates per survivor. And instead of just seeing what I would have expected, a sharp decline rate, just a constant monotone function, you have this hormesis effect where actually under low doses, you have an increase in the number of eggs per survivor, and then it decreases down here. And so this is just one example of hormesis. And then I Googled it the other day, and you can see this is not just seen in eggs per survivor, this is seen in growth rates. And I'm sure there are better people here that can talk about hormesis, where you do see this. Oh, it might not be as sharp, but it's still, yeah, maybe not, yeah. But you still have this increase and then decrease. You still have this monotone function, this hormesis effect, where I think, and correct me if I'm wrong, when you have some stressor and it under low doses promotes something like growth or egg production, and under higher doses it starts to decrease that. And so rather than just thinking about a stressor decreasing some adverse outcome, you have it stimulated at low dosages. So this is just something I just learned about. It seems, particularly it might affect, if we're looking at reproduction and looking at neonates specifically, this data set might be important. And so there's lots of other data sets on hormesis out there, just something that we might need to consider in one of our models. And if anyone has anything to add on hormesis, feel free. All right. Okay, so some important aspects to consider. This is by no means an exhaustive list. I think I just have 3 points I'm going to put up here. So anything else we can also talk about is food quality. When you're thinking about in terms of nutritional content or a stressor, they likely have different effects for different stages of growth, right? So some of the assumptions we made with the ODE model aren't going to incorporate this. We have to move to a stage-structured model of some sort if we're going to, take into account that there's different effects for the different stages. In particular, I mentioned that the earliest stages of growth, characterized by high growth rates, which are often coupled with high phosphorus concentrations or high phosphorus ratios, they might be particularly sensitive to some of these stressors. Particularly sensitive to low P food, for example. And then how is that going to couple with a toxicant or contaminant stressor at the same time? And then another question we thought of was, if you have concurrent toxicant and nutrient stressors, how is that going to influence the time to maturation and or reproductivity? If you have Daphnia, I know if you feed it low quantities of food, its growth rate is smaller, it matures later. And I'll talk about a model that shows that. If you give it low quality of food, the same thing will happen with the Daphnia, right? It's not going to have the same growth rate, it's going to mature later, subject to a toxicant. So this maturation, this lifespan of the Daphnia and the amount of time it spends in that juvenile stage seems to be highly dependent on a lot of these external factors that we are considering putting in the model. And then finally, just this little point of hormesis. That's a thing, apparently. So we should maybe consider if we need to think about that a bit more. So now I'm just going to go over some approaches to adding stage structure. And as far as I can tell, there are three obvious approaches. One is just to kind of do a first stab compartmental ODE model, break it up into a juvenile and adult. The other one is to take more of a PDE approach following McKendrick's type age-structured population models. And I have just one slide on each of these, so this is just to kind of show you that this is an approach that exists that we might want to take these directions in. And then finally, a DDE approach, so a delayed differential equation approach. This is actually the exact model that Roger showed you this morning. So I'm just going to go through a little bit more detail there because I think it's a really cool model. So compartmental approach. This is like my first stab at just making the model we discussed yesterday, the LKE model, and making it into stage structured. So instead of just, so this equation looks really similar. This is the algae equation or the prey. The only difference is now is that now you have it being fed upon by two different other populations. So I've split the Y, or I split the Daphnia, the predator population, into two equations. One's a juvenile, one's an adult, allowing us to have different growth rates for the juvenile stage and the adult stage, and different phosphorus to carbon, or C to P ratios. So we have different growth rates here within the minimum functions, as well as these ratios, theta A and theta J, are now just different. We can parameterize them differently. I haven't done anything beyond just putting these equations together, right? This is just a direction we could start in. Some big assumptions already made is that when you're a juvenile and you're growing, the growth rate in the juvenile, it's all going to maturation, right? So if you're in a juvenile stage, the only way to leave it is through this right here. And if you're an adult, you can look at the growth rate of the adult. It's all going, it's coming directly from this juvenile stage. So this is not allowing individual growth of a Daphnia getting physically larger. So we have to think about the implications and parameterizing this. Yeah, and then otherwise it's just the same formulation as the LKE model. Right here? This you're thinking this should be a J. Yeah. Down here. So this is the reproduction rate, though. So this is coming from the adult Daphnia. Yeah, but then the conversion between the two and the more from the P, and the conversion is less. Oh, okay. That's a good point. Yeah. Okay. Yeah. So these are the kinds of things we need to talk about if we start with this approach. Yeah. This might be dependent on, so this is the P to C ratio that's going to be giving you new eggs, so whether or not you start with the P to C ratio of the adult there to make that decision, or whether you go with the P to C ratio of the juveniles. Yeah, these are the same term. Oh, theta A here. Yeah. There's some decisions to make there about when you switch. your P to C ratio. If you look at the data, it's not a. So I'm looking at this data right here. If you just assume it's completely disconnected, you're going to have to make some decisions on when you're going to jump down, whether that's, the eggs come out with it. I guess the eggs would come out with this higher ratio, but but then they need more phosphorus to make the eggs. We need to think about some of these issues. But this is one direction, just to kind of do a easy extension, mathematically at least, to just making the LKE model compartmental with two predators. Okay. This is another approach which you can use partial differential equations. So this is following from McKendrick's general theory of age structure models. So you have a PDE here, and this is just a brief overview. I haven't thought about this or done any work on this at all. But populations of reproducing individuals are described at a density function. So rho, which is a function of age and of time. So that's going to be describing the population of age A at time t. Okay. And then you can always figure out the population of the number of Daphnia at any given stage by taking this integral here between ages A1 and A2. So that'll give you the total population that's between those two ages, whatever they are. So if you did that for the entire ages that are possible, and right now I'm just going to say you can go to infinity. So taking the bounds there from 0 to infinity, this is going to give you the total population. Okay. So this should look really familiar to a lot of us who have taken differential equations or math bio. This is one of the first things we see when we look at the age structure sections. So this is just another place to start, and that's all I'm really going to say about PDEs. Yeah.
Size structure is a bit more complicated. Similar structure, model structure, but I think the data, normally we give out data with size structure. It's easier to measure the length and to tell us what's the age kind of.
Yeah, so.
That's why I thought to propose that size structure one.
Yeah, so I know you're working on the size structure. So I guess a question about size structure versus age structure is, when do they mature? Do they mature are they the same size when they mature all the time, or how does that work? And when do they reproduce eggs? Do they reproduce eggs when they get big enough to get to that phase, or? Yeah. So, yeah.
Experimental evidence that says that it happens both. It can be size, get to a certain size you reproduce, get to a certain age.
Okay. Yeah.
If you go that route, there's a lot of PDE models of Daphnia out there.
Mm-hmm.
We're starting with in the late 1960s, one of the first structured population models from 65 that was actually parameterized for Daphnia.
Okay.
There's also under the Rose and the Dutch theory about in the late 80s and the early 90s, coupled with much of. So just for reference,
Yeah.
go that route, there's a bunch of stuff to go on.
So is there stuff like that under different stoichiometric constraints too? Probably not. But what about?
They're single currency models.
What about toxicant effects?
Yes.
Okay.
But it's pretty theoretical.
Okay. Yeah. Mm-hmm. Yeah. Yeah, that's it. So you're talking about, instead of just thinking about populations of age A and at time T, that have a nutrient status. It can, although we do tend to assume that it doesn't in the Daphnia, in the grazer. We try to make this homeostatic assumption. Yeah? Yeah, this, okay. Yeah. No, this doesn't have food in there at all, so we need to have that resource equation in there as well, because we need to have that be able to change in time, but also change inequality, right? 'Cause that's an important aspect.
You can couple that, you can couple equations of that sort to a food
Yeah.
equation.
Yeah, we couple these, yeah.
In the way you did in the earlier ones, and you could cover that other point, but the fact that the size structure equations generalize to any collection of high state variables. They're just state
Mhm.
a sum of reflection type terms, and in PE becomes pretty intractable, but you can write it down and solve it numerically with any variables you choose to put in, as long as you have favorable kinetics.
Yeah, okay. But in here, I had two populations with two different theta values, right? Now I have a continuous population. What are my theta values?
Oh, I think
I think that's what she was talking about, right?
right.
Yeah, so that's some things we need to decide if we have the, but you can still have a specific age is going to correlate with a specific theta value. We'll make that assumption, yeah. Yeah. All right, so it sounds like there's some good literature places to start here on age-structured Daphnia models, maybe even toxicant models, and then we'll see what we can do with the nutrients if we want to go down this route. Okay. Other questions or comments? Okay. So the other approach would be to take a delay differential equation approach. And this just keeps coming up to me because we're talking about when do they mature. It keeps being a question I keep seeing. And so when you think about maturation, I think about that delay, the maturation delay. And this is the paper that Raj Nisbet actually talked about this morning. It's a great paper if you haven't seen it. But it's small amplitude cycles emerge from stage structured interactions of Daphnia algae systems. So I'm going to go through a little bit of what they did in this paper. And they have both models and data that they collected. Okay, so this was the model. So I'm just going to point out a couple things. They're tracking the resources here, so that would be like our algae, and they're tracking the juvenile dynamics and the adult dynamics, and they're incorporating a delay in here. You see that hidden function tau of t right there. So that's going to be the delay that's getting you from juveniles to adults. Okay. And an important part of this is that it's a state-dependent integral differential equation. So down here we have this juvenile development integral constraint. That's going to be able to get us to figuring out that tau exactly there, how much time you need before you can develop. In this model, it's going to be dependent on food quantity. So how much food is available. If you have more food available, you're going to be able to mature faster. And so that's the state-dependent delay that they have here. So they're using this system here to define delay with this integral constraint right there. But then they do a neat thing where they simplify it. Because these are hard to deal with, state-dependent delays. And in particular, they do some bifurcation analysis, which you actually saw in Roger's talk. But how did they exactly do that bifurcation analysis? They did some neat tricks here where they first non-dimensionalized it, right? And then they transformed the variables to get to a fixed delay. So even though it's a state-dependent delay right now, they transform things using this equation right here. So this is the non-dimensional integral constraint that's giving you the time delay for how much, your maturation delay right there. Okay? So they changed the variables in order to get to a fixed delay right here. Okay? So using this right here, that's your time delay for your maturation, and this right here is just the pulled out expression for the Daphnia's growth rate. This is like the juvenile development rate that you're integrating over between 0 and t. So then you rewrite this in terms of phi. So now the model is now in terms of, it's on the time scale of an ingested carbon scale. So you integrate over that, and now you can redefine your delay down here to be fixed. It's kind of a neat trick there. So my question is, can we use a similar approach, but instead of just thinking about integrating over ingested carbon or integrating over ingested food quantity, can we integrate over quality as well and have that redefine our delays for us in a stoichiometric model? And then on top of that, maybe a toxicant involved as well, you know. But so delay differential equation sounds intimidating at first because you have these delay that obviously has to be state dependent. Just been thinking about food quantity, it's been shown in food quality now. But we might be able to use a kind of neat trick like this to rescale it so we actually do get to a fixed delay at the end. So these are some of the bifurcations that came out of this paper, and these are you actually saw these images earlier. So these are the interesting result where they got this coexistence of two cycles, the low amplitude cycles and the high amplitude cycles. And they characterized these are the examples of the two cycles, but they were able to characterize these with the duration of that delay. So when you're in the small cycle, you have a long delay, so you're maturing. It takes them a while to mature. And then when they are in the high cycles up here, they have a quicker delay. And they were actually able to do some experiments and then measure these things. So here you have on the bottom here, and these are also graphs you saw earlier, but here they're comparing your stage duration, which is your delay. So this is the delay. This is the amount of time it's taking those juveniles to develop. It's fluctuating because of the food resource is fluctuating, but it's staying beneath this value right here, which is the time of the cycle for the predator-prey dynamics. So this is coming from the oscillation of the dynamical systems. And so when you're on this large cycle, you're always going to be, when you're on this small cycle, you're always going to be smaller than when you're in this attractor right here, the time you're taking delay is always going to be small. I'm getting mixed up. When you're on this small cycle here, the time you take to mature is always going to be larger than the population cycles, right? And that's what you see right here. Whereas when you're on the large amplitude cycles, the time that you're taking to mature is always going to end up being smaller than the duration of the cycles. And then this is the experiment that he mentioned that they did. So they had tanks of algae where they grew them up for 200 plus days, tracking them. And then they also did this neat thing when they were able to take them out and look at individual developments. So they were actually able to have these tanks of Daphnias and then also keep track of that delay and like get a measurable output for that delay. Compare it to the cycles that we saw earlier, because they also measured the cycle period by taking algae out of the tank as well. So they measured the algae population fluctuating over time. Again, this is over 250 days, and then track that with measuring the juvenile development delay, the amount of time it takes. Okay? So this is the data that he showed you earlier. And they did find these large amplitude cycles and these small amplitude cycles right from the data, which matched the model that they had as well. So this is the data that he showed you earlier. This is some more here where it's color-coded to show you what cycle it's on, whether it's on the large amplitude cycle or it's on the small amplitude cycle. And the reason they were able to define it so clearly is because they were able to actually go in and measure the delay, amount of time it takes for the juveniles to mature, and then categorize it as what cycle it's on by comparing that to the amount, the cycle of the amount of time for the predator-prey cycle. So if it was greater than 1 versus less than 1, looking at that ratio, they were able to take the data and actually kind of figure out, okay, because of the time it took you to delay, I know you're on this small amplitude cycle, versus the time it takes you to mature, I know you're on the large amplitude cycle. So that's just kind of a neat approach. I think doing the delay differential equation, there's a lot of ways that we can continue that. And in particular, that was just looking at, it's a neat model where they're looking at a maturation delay that's dependent on food quantity. Can we extend that this afternoon to be formulated in terms of food quality, or in terms of a toxicant that might influence your time to maturation? If we do that, do we have data that we can use for that? So what data is available? There's a lot of Daphnia age structure data, a lot of Daphnia tox data. What data would be useful for this particular exercise is something to think about. And so I'm envisioning the stage structure breakout session to be either talking about whatever direction we'd like to go in. These are 3 directions I identified. Kind of starting with that compartmental ODE model, starting with a PDE approach, or going with the delay differential equation approach. And we can discuss what are the pros and cons of each of these and what directions we want to take this in. And then finally, I think I talked about this a little bit, just what data is available. are there appropriate data sets out there, or do we need to suggest future experiments to capture the data we need if we wanted to really capture this maturation, or the stage structure model completely. That's all I have for that stage structure ideas. So any thoughts, discussions from you guys? And I think you need the, you need the mic because it's live streaming. Yeah.
I have two questions, but let's start with the one delay, previous one, the slides. You have the 2 cycles. When the maturation time is large, you have small amplitude, right? But when you have a smaller maturation, which is delay, delay is smaller, actually you have a larger. So in some sense, it seems actually the larger delay is more stabilize the population, right? Stabilize.
If I go back to this bifurcation diagram.
Yeah. So my question is, I know we in our work also we have been using different type of the delay. So usually what we observe probably is the larger delay actually is more destabilize the system, but not always. But when larger is the delay.
Because this E to this sort of modulation of the birth rate, this E to this term, S
Right.
theta. Yeah, so that's sort of like a dampers the population, and so that's actually stabilized. So yeah,
So it depends on the model.
yeah,
It depends on the model. So that's what I'm asking. So what kind of type of model actually usually you have this observe this type of?
If you derive like what they derive from the PDE, you will always have this modulation term, and
Okay.
so almost usually you will have larger delay end up stabilizing because you have a much smaller population,
Okay.
sort of, and that sort of dampers.
Yeah. Okay. Thank you. That's my question. So the
Correct.
previous one, delay. Sorry, helping it. So this one, yeah. Have you tried this system yet? I mean, how did you study stability? Because have you tried to? Do you have a concrete example to study the stability? I mean, let's say you have equilibrium point. How do you study the stability?
You mean like to
Just-
get this diagram?
Just in general, the system you show, the previous one.
Yeah.
Sorry. Yeah, this one. Do you have a specific example you have start to look at the stability analysis?
Specific examples. So I know.
Oh, okay. But
So-
okay, it's maybe I can we
They
can talk
had,
later. Because
they had and Roger can probably add to this, but they computationally were able to. Oh, let me go back to that. But they were computationally able to get this bifurcation. So they had this stable equilibrium here.
oh, so basically, this is coming from the model you.
This
were-
is from the model. Yeah. This,
so you present.
so they. Yes.
So are you able to do some theoretical analysis? That's what I'm
take-
asking.
Please jump ahead.
My answer comes in 2 parts. My answer would come in 2 parts. That for any system of delay differential equations, or pretty well any system, whether with a fixed delay or a variable delay, you can get the linearized stability analysis by essentially a variant of the standard techniques. You linearize about equilibrium. The characteristic equation is no longer a polynomial. It's it's a sort of quasi-polynomial with a mixture of exponentials and polynomial terms, and that means it can have multiple roots. So the analysis often of the characteristic equation has to be numerical, but the philosophy of the approach is
The same as before.
pretty well identical. For this type of diagram, there are probably people here that have better techniques than we used. We did it in 2 ways. One was when you have a single delay, like using the trick you described, you can use pretty much the canned software that exists for bifurcation analysis of delay differential equation. For the PDEs, in the only example we did, we discretized it to maybe something like a mesh of 170 or 190 points. I forget the number for with the postdoc who did it, but essentially what you could get in a PC. And then you used one of the standard ODE bifurcation packages and checked on and
and checked on the sensitivity to the discretization, and that gave you a cheap and cheerful way of generating pictures like this for the PDE.
So
But
you
I'm
just-
sure people like you or
But you
Yang could do better.
So you just discretized the PDE to a bunch of OD, like a whole bunch of ODs.
A whole bunch of ODEs.
Okay.
Yes. But either, I mean, the first thing I described was in a sense relates to the theory. The second is theoretical only in the sense that that software is related to underlying bifurcation theory. But either way, I don't think it's an impediment to progress.
Yeah.
Okay, good. Thank you.
Okay, so two things. The one thing is that, well, first of all, the Hormesis thing was also new to me, very interesting and complicated to take into account. Another sort of behavior that we've seen that we might need to take into account as well is the fact that what part of your life cycle you are exposed in can actually determine not just effects for that part of your life, but also for later on in life. So juveniles get exposed to some small amount of a toxicant when they're young. They then have less response later on in life. So anyway, there's like these time-dependent
Delays based on the toxins.
yeah,
that-
depending on when you're exposed, because you start to develop resistance and things like this. But
Okay.
so that's something else that may or may not work its way into the stage structure stuff is the best way to approach that, I think. But also, I just wanted to point out everything in here is in continuous time, and so there are some discrete time approaches that we might be able to look into too, such as like integral projection models or matrix projection models if we want to start going that route.
Yeah, that's a good point.
Yeah.
Yeah, I don't have questions. I just want to respond to Yun and Roger. I think for Yun's question, I think it's just it's a bit mathematical. I think you use Yang's paper. So you have SN just bend back. So you have eigenvalues with positive real parts, then come back to be negative again, kind of. So that's, yeah.
Introduce new variable. When you introduce new variable, I think one of eigenvalue will be equal to 0. And then, but we can talk about later.
Yeah.
Yeah,
because-
so we're always looking for the eigenvalues with 0 real part, right? Or you mean the neutral case with the
No,
0
it
eigenvalue?
will be when you introduce the new variable, I think.
Or this one?
Okay, maybe I'm just yeah, okay.
Talking something else? Or-
Maybe something else.